Hey, welcome back to the Tool and Cutter Grinder. Today I want to talk about the backrelief attachment of the S1 grinder and also show it in operation to grind a 90-degree countersink. So let's look how this goes together. Okay, while we're here I was thinking I could also show you the infamous helical generator setup on the Deckel S1 grinder. The problem on the helical generator on this machine is it's a pain to set up, and you do not have a freely adjustable pitch. You have to turn these pulleys here according to the pitch you want to grind or the helical angle you want to grind. There is a formula in the manual how to determine the diameter of this pulley. Then you turn one and you're good to go. It works, but on a Deckel S11 you can set the helical angle just by means of a sine bar. That's way faster, way easier. This is a very ancient way of doing it. But it's here and I have it. I'm probably never going to use it, but I have the option to if I need to. And the way this works is it has the same gearing setup depending on the pitch you want to grind. Under this cover then the backrelief attachment, and you have a pulley here. You have this T-shaped holder here, and there's a steel cable. It looks like a guitar string, a metal string, and it's wrapped around this pulley once, and then it's tensioned with this knob. And when you move this upper slide, the steel cable spins this pulley, and through the gearing in this head creates the rotational motion. And that way you can grind very small tools with helical flutes without having to resort to a tooth rest. Tooth rest only works on end mills maybe larger than 10 millimeters, or you have an air bearing setup and you can probably go smaller. But this is a forced helical generation and you're independent. And this basically takes no skill once it's set up. You just move it back and forth and the helix angle is always fixed the same. This also allows you to index the cutter. Let's make a blue mark here. So you grind your first flute like this. You grind it and you take your indexing back here. Index it, for example, 90 degrees. Then you grind this flute and you index, you grind the next flute. That allows you to grind helical multi-flute tools. And if we add an adjustable angle plate in here that tilts this whole head in relation to the slide here, then we can also grind helical tapered multi-flute tools. That's a mouthful. That's, by the way, this plate here. There's a dovetail here, allows you to, I think it's clamped right now, allows you to mount the dividing head here, mounts to this rail here, and allows you to grind tapered tool with a helix angle. I got this off the internet, and it's a little bit banged up, needs some work, but it's generally okay-ish. Needs some surface grinding probably. And this allows us to do helical grinding if we really need to. And also when you do helical grinding you need some way of finally adjust the orientation of your flute, and for that we have this knob back here. And this moves this whole arm with the steel cable along, and adjusts the rotational position of the flute in relation to the grinding wheel. So let's take this apart and look how all this is put together. So I don't have you to show the whole setup. This knob here untightens the steel cable, and then we can unwind it, pull it off the pulley. Pull this back a little bit. Here's a steel cable. And then we can, for storage, just rewind the cable back on this spring-loaded tensioner here. We can move this head out of the way and pull this part here out. So here, this is the steel cable. It's guided through these two pins, and here's the cable reservoir. There is a spring under it, so it doesn't uncoil itself once you loosen the thumb screw here. Then you pull out as much cable as you need, wrap it around this pulley, and tension it back on. It's that simple. To take this further apart, we undo this screw, and this washer and this long screw comes out, and we can pull off the pulley. And we can take out these additional screws here. And underneath here we have the gearing for creating certain ratios of pitch to rotation. This is currently the setup 18 to 72 gear teeth to use the back relief attachment with a shallow relief angle. These gears stay here to be used with the back relief attachment, and this cover goes on. Screw back in. Just like this. Then this is the cam for the back relief. Screw and washer. Tighten this down and we're good to go. As you can see, the cam rotates along with the spindle, and this cam is gradually falling off. This is not a constant curve, this is falling off. This is an increasingly steeper curve. To finish mounting this attachment, we push the indexing head back. We have this piece here, dovetailed with a cam roller. This goes in here. Then you eyeball the center of this roller with the center of rotation of the cam attachment, which is about like this. This is adjustable because the cam can go in the other position too, or if you have a swivel plate under this head, this whole cam has to move out further. And that's the whole setup of the back relief attachment. The function of the back relief attachment and the helical generator are basically the same, only that the back relief has a very, very low axial motion in relation to the rotation. So as you can see, when I do something like quarter of a turn, that's about a millimeter of movement on the axial position here. The way this grinding works is we spin this back and forth to the back relief. This just moves in, so we are contacting the grinding wheel, and my actual depth of cut is set with this upper small slide here, which moves the roller guide in and out, and this advances also the dividing head towards the grinding wheel. There we go. We ground the first relief surface here, cleaned up completely. now we need to index to the next flute. For that we bring our stop up here in contact with the roller, and we use our direct indexing feature here, back here, to index 120 degrees. 3 flute cutter, 360 degrees divided by 3 is 120, so that's our increment that we have to index. Did all the grinding, and as you can see, looks like a countersink to me. This also allows me to create countersinks from scratch out of solid stock. If I need for some odd reason a properly ground countersink with a 60 degree, or 60 degree you can buy, let's say 59 degree, or I can modify existing ones to a odd angle. Let's check the back relief that we ground with an indicator. That's always a good idea to do. For that we take a dial test indicator, we bring it in contact with, first with the larger diameter of the cutting portion of the relief surface here. Give it a little bit of preload. Starts out at 40, then it drops over the distance of the relief surface constantly off. This is beautiful. This is really nice. The geometry between the cam and the relief angle is, quite frankly, a little bit complicated, but Deckel, when they sold this machine, was kind enough to provide a setup sheet. We will look at that in a second. So we start here at the highest spot of the cutting edge. This is the cutting edge, 22. Then it drops off constantly until it falls into the next flute. This is just beautiful. So yeah, I'm really happy that I finally have the ability to do this grinding. Preferred method is to grind the OD, this face here, the back relief. This is preferred. You can regrind the countersink with very little material removal that way, and you can regrind it very, very often. But another way, if you don't have a back relief attachment, is to grind this inner surface here. And I did this on this countersink previously. The problem is that you have to match the original surface, and you have to radially advance it into the grinding wheel to keep the overall geometry of the countersink. That's fairly hard to set up. You don't need anything special, you just need a dividing head that can move radially into the grinding wheel, but getting that surface correct is quite tricky. There is not much to indicate against. Then you dress a grinding wheel with a radius and you move through there, grind like this. Okay, normally this is not necessary what I'm doing now. I'm regrinding the cutting edge in the flute of the countersink. I'm doing this because I previously reground this rather badly, and that leads to a very poor performance and a tendency to chatter. So I'm doing it now half decent properly. And grinding the flutes on a countersink is really tricky, but that's the setup here on the S1 grinder. It's swung over 10 degrees, it's tilted back about 22.5 degrees. So the floor of the flute is leveled. And I'm basically like on a surface grinder, I'm grinding like this. This floor surface of the flute inside here, down here, is indicated level with the travel of the table. And to do our grinding, we drop down the wheel to the floor of the flute, and then we rotate the cutter into the wheel to grind material away. And we do that by using the fine adjust down here. Okay, you all probably want to see how this darn thing cuts. So let's go. I have a piece of, I think this is 6082 aluminium, and I pre-drilled a bunch of 6mm holes, and let's see. Let's go through the results I got with this countersink. I had to modify the grind once again, and I will show you in a second why. This was my very first attempt with the flute that I reground a month ago and kind of buggered up. And after grinding the Backrelief, I got this horrible chattery mess here. Really terrible, completely useless. So then I fixed the flute. That's what you saw me grind with the wheel in here. And I got this result. This is what you saw me doing on the mill. Orders of magnitude better, but still kind of not ideal. There is still chatter, and it's a little bit out of round if you look from the top. That's not ideal. I wouldn't do this on a customer part. A bad countersink just looks like a bad countersink, no doubt about it. But I modified the grind again, and now I get this result. And this is silk smooth in here, super smooth, exactly the grind finish on the tool, and no chatter whatsoever. If you look top down into these countersinks, that's how they should look, not like this. This is really nice. I like this. So, and why did this happen? When you look at this cutter, the cutting edge needs to be in line with the shank, like this. And also, this cutting edge needs to go through the center of the tool in front here. And you grind this by, you adjust it like this. So the cutting flute is in line with the shank. Then you rotate it until the surface in here is vertical, so you can run with your grinding wheel and side wheel it. And when you set it up that way, you get an angle here. That's off axis to the shank of the cutter. But still, this line needs to go through the center of the tool. This is really hard to explain. And when you set this up, it's relatively easy if you know it. You look down the straight edge on the side here. This goes basically through the center of the tool here. Why this is uneven? Because I chopped off the end just on the belt sander, and this is not remotely square. This is just to clean up the end. And so this needs to go through the center of the tool on the tip here. But when I did these countersinks here that were not ideal, it was more like this. I was heavily behind center, and that makes the tool cut super aggressive. It cut very well, but it wanted to grab all the time. And I kind of noticed that when I filmed it, but didn't want to tell you. So I went back to the grinder, I fixed the cutting edge, I ground it so it's now in line with the center here. And now I get this result here. This has gotten a fairly complicated video. It started out with the helix and Backrelief attachment with a little bit of grinding on a countersink, but the countersink didn't work because I had previously messed it up. I fixed it again, and now we're here. So let's look at a quick CAD drawing of this countersink, and I think then we can get finally to an end. Okay, we're here in CAD. I have a soon-to-be countersink here. A countersink starts basically as a blank like this. This can be either turned and ground or directly ground from solid. Starts basically as a revolve. Half the profile rotated around the center. Then we add a flute. This is sketched as a triangle. That's this red shape here, or this highlighted shape here. And this hits here on center line and goes all the way to the front. It doesn't go to the center, otherwise it creates a very weird geometry. So now we need this 3 times. Looks already like a countersink, but this would cut like really bad. I'm not modeling the back relief on the taper. That's not interesting. We're just interested in the flutes right now. To make a countersink work properly, we need a positive rake. Otherwise, they don't work very nicely, which I found out the hard way. I'm using the draft function. This is normally used for adding draft to a casting, but it works also for a cutting angle. I'm going for 10 degree. Boop. And there is our 10-degree back rake. And the reference for this back rake angle is this axis here. I have a plane, a 3D plane going through that edge and square to the world. And the back taper here unfolds from this edge to the back. We can also increase this back angle or decrease it. But let's keep it at -10. This seems to work quite well in reality. Let's align the countersink like this. As you can see, The shank is horizontal and the main cutting edge here, this is also perfectly in line with the shank. It's oriented in the x-axis. That means that once we use this countersink, it will create a true 90-degree countersink. But you can see that the cutting surface has a back rake. It goes, when we switch on wireframe, it goes back beyond the cutting edge. And when we spin this thing now, until we get this surface here standing up vertically, it looks like the cutter has a shear angle, and it also has a shearing action. But in reality, it's a straight cutting edge that's perfectly in line. It's tricky. Cutting tool geometry is really tricky. And this is the orientation we're going to grind this. We need this theoretical angle in relation to the center line of the cutter. And we can get that with a sketch. The sketch is in line with the shank. These are projections of the shank ends. This line is the center line of the cutter, and I just measured from the cutting edge to the center line, and that's 9.85 degree. So basically 10 degrees, close enough for this application. And that's what we need to set to turn the head of the tool cutter grinder over to grind this flute properly. Okay, this is the countersink with the final adjustment of the cutting edge. And as you can see, it cuts, now it's cutting like it's supposed to cut. No chatter, leaves a beautiful finish. Just like the example I showed you previously with the very, very nice quality of the countersink. I hope you enjoyed this brief demonstration of the Backrelief attachment and also of the helical generator of this machine. As you saw, the helical generator is not the most user-friendly thing in the world. But the Backrelief attachment, this is easy to set up. This is like 2 screws and we're ready to go. No steel cable or something like that to wrap around the steel disc that slips off 100 times. And it's useful. Countersinks, counter bores, step drills, center drills are also Backrelief ground on the 60-degree tapered section. That's also possible with this attachment. The lead-in on tabs is ground with an axial Backrelief. So this can do a lot. And you can also use this in a different way to do radial Backreliefing. That would allow me to do something like a gear cutter that is backreliefed. But I have to investigate how that's done. You have to mount it 90 degrees offset, and I'm not entirely sure how that works, but there is a technical bulletin from Deckel describing that process. But apart from that, very useful. Helical generator probably not that much. Hope you enjoyed seeing this ancient, obsolete piece of technique in use. Thank you all for watching, and I'll be back.